Okay, let's start with example of conjugate prior. The first one, binomial plus beta. Statistical model is a binomial distribution. After n trial, we observe the X success. And here, Q denotes the probability of success. For example, X ranges over 0 and n. For this statistical model, the conjugate prior is given by a beta distribution. The support of beta distribution is between 0 and 1. And here, BA comma B denotes the beta integral. This is a normalizing constant. And A and B are positive constants called hyperparameter. And using this kind of beta distribution as a prior distribution, then we obtain the conditional probability of Q after X observation, which is again, the posterior distribution becomes again beta distribution. And just we replace hyperparameter A and B with A plus X and B plus N minus X. N minus X denotes the number of failure. So this is a convenient formula to calculate posterior distribution in this case. Okay, let's go to the next example. Next example is a combination of Poisson distribution plus gamma distribution. A statistical model is given by a Poisson distribution with mean parameter lambda, which is a positive constant. And its probability function is given by this form. Lambda x power over x factorial times e minus lambda. This is a normalized constant. And x ranges non-negative integer. For example, x is a number of car accidents. Okay, now we have a statistical model, Poisson model, then the conjugate prior of lambda, which is positive, and it is given by gamma distribution. Gamma distribution has the following form. And here, again, A and B are positive hyperparameter. And using this gamma distribution as a prior distribution, then we obtain the posterior distribution in the following form. This again, gamma distribution, but we replace hyperparameter A and B with A plus X and B star, slightly changing from B. Again, this is a very convenient formula to calculate the posterior distribution for this statistical model. Now let's go to the final example. Normal distribution plus normal distribution. Statistical model is given by a normal distribution with the mean parameter unknown, and the parameter variance parameter S is known here. And we here write the symbol of distribution, normal distribution, which is denoted by N, capital N, theta gamma S. Theta denotes the mean parameter. For this model, the conjugate prior of the parameter theta is given by normal distribution. Here, Xi and V are hyperparameter. Xi is a real, and V is a positive constant. Using this form, then we obtain the posterior distribution, and this is again normal distribution. And here, the parameter W and theta, which are calculated using this formula. So the hyperparameter Xi and V in the prior distribution replaced with W and theta, which are calculated under observation. Here, Xn bar denotes the mean of data. Now let's see the potato posterior distribution using the conjugate prior. Here we deal with a binomial model as an example. First, in this binomial model, we set a prior, the uniform distribution. In other words, we set in the conjugate prior A equal B equal 1. Then, we obtain n equal 5 and x equal 4 observation. The posterior distribution of the parameter q is given by this beta distribution. We have used the convenient formula to calculate the posterior distribution. And this is a polynomial, and we have drawn the graph of this posterior distribution. The right above panel shows this posterior distribution. Dotted line denotes the posterior. So we can see the peak around 0.8. This is a maximum likelihood estimate of the parameter q, because we obtain, after 5 trials, 4 successes. 4 over 5 is 0.8. So first, we have no information on the success probability q, so we set a uniform distribution, which is denoted by this black line. This is a uniform distribution over the parameter q, and after observation, we obtain conditional distribution, which has a peak around 0.8. This single peak appears. Now we consider we have much data, 50 trials, and we obtain 40 successes. Then we can calculate the posterior distribution of the parameter q. Again, we obtain the beta distribution. And in the right below, we have drawn the graph of this posterior, which is denoted by this dotted line. Again, we obtain the peak around 0.8, but we can see sharper peak we get. And basically, we have more and more data. We obtain sharper peak around the estimate of the parameter q. Okay, so this range denotes a certain uncertainty on the parameter q. This is the meaning of the posterior distribution. Now let's summarize this section. We briefly review elementary Bayesian statistics. And first, we assume data distribution, which is called a statistical model. And here, we assume data X or observation X comes from a certain probability distribution, which is specified by a certain unknown parameter, theta. This is a basic assumption. And in Bayesian statistics, we set a prior distribution or probability distribution over the parameter theta. This is an important point in Bayesian statistics. And then, if we set a prior distribution and statistical models, automatically we can calculate conditional distribution of the parameter theta given data X. This conditional distribution is called a posterior distribution, or shortly, posterior. And this is very fundamental to Bayesian statistics or Bayesian data analysis.